Okay, let's review some of the material we presented in the previous lectures. So we looked at implementing logic gates with perceptrons. So we can use the perceptron to implement the basic logic gates and or and not. And all we need, so if we can implement an and, or, and not, we should be able to build any function, any logical function from these three operations. So all we need to do is to find the appropriate connection, weights and neuron thresholds, or the bias to produce the right output for each set of inputs for these functions. As I said, it is known that we can construct any logical operation from this and or. But the resulting networks will, however, require much more complex architecture than a simple perceptron. So if you want to build a complex logic function, even if you decompose it into these three basic operations, it requires a lot more work to do. So for example, in each case, we have inputs in and output out, and we need to determine the weights and threshold for these three functions. It is easy to find solutions by inspection. For example, if we have a perceptron with these two input, in1 and in2, and these weights 1, 1, and the bias 1.5, we can see that this configuration of the weights and the bias is able to solve the problem of the end function, or so just to double check. So for example, if in1 is 0, in2 is 0, so 0 plus 0, 0 times 1 plus 0 times 1 is 0. It is less than 1.5, so the output is 0. If we have 0 and 1, so this is 0 and 1 is less than 1.5, so the output is 1. The same thing for 1, 0. But then when we have 1, 1, 1, 1, so 1 times 1 is 1, plus 1 times 1, so you have 2 is greater than 1.5, so the output is 1. And you can check also that these weights and biases work for the not and or function. Constructing simple networks by hand is one thing, but what about harder problems? For example, what about the XOR function, where this is the truth, the truth table for it? So how can we find easily the threshold, the weights and the bias? How long do we keep looking for a solution? We need to be able to calculate appropriate parameters rather than looking for solutions by trial and error. Maybe there is no solution, just like in this case here. So each training pattern produces a linear inequality for the output in terms of the input and the network parameters. And these can be used to compute the weights and the threshold. For example, if we look at if we look at this, if we have a network like this, so out is the sine of W1 in 1 plus W2 in 2 minus theta, which is the threshold or the bias. So we have two weights, W1 and W2, and the threshold theta. And for each training pattern, we need to satisfy this equation. So for example, for the end function, so when for this equation, if we replace this in 1 and in 2 in this equation, we have W1 times 0 plus W2 times 0 minus theta should be less than 0, should be, because we want an output to be equal to 0, so it has to be less than 0. And the same thing for the second input, so W1 times 0 plus W2 times 1 minus theta, and then we want it to be 0, so it has to be less than 0. Except in this case here, which is W1 times N1, which is 1, plus W2 into, which is 1, minus theta. And because we want it to be equal, the output to be equal to 1, so this has to be greater or equal than 0. And so this simplifies to theta positive. This inequation becomes a W2 less than theta. This one, W1 less than theta. And this one is the sum of the weight greater or equal than theta. If we want to solve this set of inequalities, it is easy to see that there are an infinite number of solutions for this. Similarly, there are an infinite number of solutions for the not function and the or function. So we can solve these three functions just using this approach. What about the XOR function? So this is the truth table of the XOR function. If we follow the same procedure, we find we need to solve this set of inequalities. And you can see here that the second and the third, so we want W2 to be greater or equal than theta, W1 greater or equal than theta, but their sum is less than theta. So these are incompatible with the fourth. The third and the second and the third are incompatible with this fourth inequality. So we cannot solve the XOR problem with just one perceptron. We need more complex networks, for example, that combine together many simple networks or use different activation functions, maybe different thresholding, different transfer function. So simply this cannot work. It then becomes much more difficult to determine all the weights and threshold by hand. We don't want to do it. So these weights instead should be adapted or changed or modified using learning rules. This is what we saw in our previous lectures. So we have to either consider different learning rules or more complex architectures or a combination of the two. Again, this is the decision surface for perceptron. So this is this problem can easily be solved just with a linear discriminant function. So it's linearly separable. This is the case of the XOR. It's a non-linearly separable. The perceptron is not able to solve it. Okay, thank you.